Hey, good afternoon. In this video series, we're going to be dealing with an adiabatic flame temperature. And in this video in particular, we're going to be explaining how the moles of each species in the feed and product, so with the reactants coming in and the combustion or the products from the combustion reaction, how they're determined from the reaction stoichiometry and given that we're going to have excess air. So let's go ahead and first walk through our situation, which is that we're going to have a Bunsen burner here, and we're going to pretend this is the world's greatest Bunsen burner and is able to not have any heat loss through the sides of the Bunsen burner, that we're not having any work performed, and we're not having basically anything that would cause heat loss isn't going to be happening here. And so we have an adiabatic situation, and we're going to end up having our natural gas, which is our fuel, and we're also going to be feeding that with our air, and then these two are going to come and they're going to mix together before hitting our flame and causing a combustion reaction. Let's talk a little bit about what is happening in this situation. Well, one is for air, we are going to have, well, with air, there's a 21% mole ratio, roughly. It's more like 78% of nitrogen, 21% of oxygen, and 1% of argon. But for this case, we're just going to go ahead and write 21% for oxygen and 79% for nitrogen. So that's going to be our air coming in, and excess air we will say as 20% excess air adding into our mixture. So that's going to help the overall mixture because it's not going to end up mixing perfectly in our Bunsen burner. So one is that we have adiabatic, which means that there is no heat loss that is occurring. Two is that this is a steady state system. And what does steady state system mean? It means that we have zero changes with respect to time. Now, why does this matter, and what does this inform us of? What this helps us see is that the enthalpy coming into the situation, coming into the Bunsen burner, has to equal the enthalpy leaving. So the enthalpy from our reactants has to equal the enthalpy leaving our situation. Why? Because it means that there's no changes with respect to time, meaning that we can't have more energy that enters the system and more energy keeps building and building and building if it's in a steady state. And we also can't have more energy leaving the system and leaving our system continually with lower energy states, because there's no changes of energy with respect to time. And so let's go ahead and just write out what that looks like regarding the enthalpy of our situation with our steady state. So that is going to let us know here that our enthalpy change is going to be 0. So our enthalpy coming in, so our dm enthalpy coming in minus our enthalpy leaving the system equals 0. And so, just again to clarify, this means that our total enthalpy coming into the system, the total enthalpy coming in, the internal energy coming into our system, equals the energy that then is leaving the system. Now, the next thing we want to cover is what is our natural gas consisted of. So here we have our natural gas, because in a combustion reaction is natural gas and air, and then when you burn those two reactants, the products of that are going to be CO2 and water. So first we'll go ahead and write out our natural gas, and here we're going to have a 95% mole concentration of methane which is CH4. We're going to have a 4% mole concentration of ethane. So we're just burning alkane groups here. And that's going to be C2H6. And then lastly, this is the composition for fuel, 1% of propane, which is C3H8. And then when the natural gas burns with our air, and again our air is, we're going to do our 21% ratio of oxygen to our 79% ratio of nitrogen. And the products of this, products of a combustion reaction, let me go ahead and write that out, of a combustion reaction are CO2 plus water, and in this case we're going to have our excess air as well, plus excess air. And another thing to consider here is that we're going to have a 79 to 21 ratio of nitrogen that is leaving. And the reason we want to make note of the nitrogen in particular here is one of the products is, even though the stoichiometry is going to be the same on both of our reactions once we draw it out, on both sides of the reaction I should say, the nitrogen leaving as a product is going to be at a much higher temperature than the nitrogen that was entering in the system. So we want to just make note of that there. So let's go ahead and balance out or write out our stoichiometry, and then balance that out for part one of this video to show, again, going back to here, explaining how the moles of our species, basically of the feed, the natural gas in the air mixing together, coming in and burning with the flame and producing the products, how those are determined from the reaction stoichiometry with the excess air in mind. So let's start with methane as our first reaction. So here we have CH4 plus O2, so for our oxygen, plus, every time we've got our oxygen, we're going to have our 79 to 21 ratio mixture of our nitrogen. Now this is going to then burn in our Bunsen burner to produce carbon dioxide and water, and our nitrogen at the higher temperatures. And then again, what we need to consider is that we have excess air. So let's go ahead and balance out our stoichiometry now for this equation. So we're going to have our 1-to-1 ratio with our carbons here for what is getting burned, but going to then set our hydrogens. That would give us a 2 on this side, which then balances out for our 4 hydrogens here. Then we have 2 oxygens, 4 oxygens, and then that would give us our 4 oxygens on this side. But we have to also remember our excess air. So this whole situation, oops, I forgot to include, if there's 2 of that, that means there's 2 times this ratio here. Let's go ahead and do that. There we go. Now our excess air is 20% excess air. And so let's go ahead and put that in here, which is going to be 1.2 times our air coming in there. And then what that's going to look like on this side is our one, I should have given myself more space. This looks a little bit sloppy, but then 1.2 times our nitrogen that is going to be leaving. Now, if we've already accounted for some of our oxygen here and here, meaning that would then leave us with, if we've got 20% excess air multiplied by our 2 moles of oxygen coming in as a reactant, that leaves us with 0.4 O2 as excess air. So everything in the blue here is compensating for our excess air coming into our mixture. So that is for methane. Let's go ahead and write out for ethane. And it's going to be largely the same process. Actually, pretty much the exact same process, just different numbers because of the different ratios and amounts of carbon here. So we've got C2H6. Let's see, make sure we give ourselves more space this time. Let me just go ahead and write in our excess air now. Save for that space. Then we're going to have our 79-21 ratio of nitrogen included with our excess air. Again, that is going to burn. Then we're going to have our CO2 that is produced along with our water, along with, again, we'll account for whatever it balances out as. It's going to be that excess air of 20% plus, well, we won't be able to get this coefficient yet for the air until we balance out our equation. There we go. Let's go ahead and balance out our stoichiometry now. So we've got 2 carbons on this side, requires 2 carbons on this side. We've got 6 hydrogens requiring 3 hydrogens here. So then when we add up our oxygens, that is going to leave us with 7/2 oxygen, and as well as 7.5 moles of our nitrogen at that ratio, as well as there. So then 1.2, so 20% of excess air of our 7/2. Let's go ahead and multiply that, see what that is. 3.5 times 0.2 gives us 0.7 moles of excess air that will be leaving. Now our last equation is for propane, for our stoichiometry here. And this will be able to dictate, including our excess air, all of the moles that are coming in and the moles that are coming out according to the stoichiometric equation here, balanced out. So propane is C3H8 plus, let's again get our excess air counted in for now. We don't know what our coefficient is yet. And we got our nitrogen. Again, this is going to burn, and it's going to produce our carbon dioxide, our water, plus our excess air, whatever the ratio is going to be for our nitrogen. I gotta write smaller, but here is our excess air. Again, everything in blue is the excess air. Now let's balance this out. So we've got 3 carbons on this side, leaving us with 3 carbons on this side. We've got 8 hydrogen on this side, leaving us with 4 to give us our 8 hydrogens on this side. Now this gives us 10 oxygen. Oops, 10 oxygen, meaning 5 oxygen. So then 5 at a ratio there, and then that gives us 0.2 times 5. 0.2 times 5. Oh, just 1. It bounces out at 1. We don't have to write it, but just to note that we are considering it 1 mole of excess air for our propane. And so this will conclude part 1 of this video series dealing with an adiabatic flame temperature, and specifically showing how the moles of our reactants coming in with our natural gas composition and our air mixing together, and how they're determined by the reaction stoichiometry, including in our excess air that we've included. Thank you.